Hello, we are Jordi Carreras and Elena Druguet. We will talk about shear zones and related structures based on the Cap de Creus case study. We will emphasize their geometry and kinematic aspects whose interest goes beyond the regional concern.
This is the outline of our presentation. We will give a brief regional setting. Then we will focus first on shear zones in isotropic rocks, exemplified by the southern shear belt in Rosas Pluton, and second on shear zones in foliated rocks from the northern shear belt. From the last, we will emphasize their geometry, kinematics, shear zone-related structures, and discuss models for their development.
This video is dedicated to Peter Huddleston in the year of his retirement. The Cap de Creus Peninsula is located on the easternmost part of the Pyrenees. The Pyrenees is an alpine chain consisting on a Variscan basement of Neoproterozoic to Carboniferous rocks and a Mesozoic to Tertiary cover sequence. Rocks outcropping in the axial zone belong to the Variscan basement.
The pre-Variscan sedimentary sequences and magmatic rocks were submitted to Variscan polyphasic tectonics, a low-pressure, high-temperature metamorphism, and associated igneous intrusions. There is some controversy about the effect of alpine tectonics in the Variscan basement, although to us, all penetrative deformation structures are related to the Variscan orogeny. Cap de Creus corresponds to the easternmost outgroups of the axial zone. A network of predominantly dextral reverse shear zones extends along the central and eastern axial zone and North Pyrenean massifs. This shear belt and associated mylonites developed at green schist facies retrograding metamorphic conditions. They represent an event of deformation localization during the progressive evolution from transpression to strike-slip tectonics at the end of the Variscan orogeny. Such event will be referred as D3 deformation phase. Restoration of the Eoalpine sinistral displacement and rotation of Iberia along the North Pyrenean fault allows us to outline the former trend of the mylonite belt that we interpret as late Variscan. In a wider context of the Variscan orogeny, the Cap de Creus shear zones represent sectors where the crustal scale transpression is partitioned into domains of localized shear.
In the Cap de Creus Peninsula, two shear belts exist, both located in crystalline rocks. The southern one affects mainly granitoids, while the northern one traverses medium to high-grade schists and associated intrusive rocks. These are mainly pegmatites. We will start with the southern shear belt, where shear zones affect Variscan granitoids, mainly granodiorites and applied pegmatite dikes. Where unaffected by the shear zones, granitoids are almost isotropic or slightly anisotropic due to the presence of a weak magmatic foliation.
The Rosas Pluton recorded a range of structures related to syntectonic cooling of the granodiorite, from ductile high-temperature homogeneous deformations to low-temperature localized shear zones and late brittle fractures. Thus, rheological changes occurred during Pluton cooling, which induced a progressive increase in deformation localization. Our findings are in agreement with the AMS studies performed in other Plutons of the Pyrenees by the structural geology team from Toulouse.
This picture shows an ideal millimetric to centimetric thick shear zone in isotropic or weakly foliated rocks. The foliation pattern records sinistral heterogeneous shear. Shear zones are moderately dipping to the southwest with subhorizontal stretching lineations indicating a predominant sinistral shear sense. Folding of the entire shear belt may be related to progressive shearing.
A rather homogeneous magmatic to high-temperature fabric affects the enclave-bearing granodiorite. This was subsequently followed by leucocratic diking at a high angle to the ductile fabric. Thus, both the magmatic fabric and the dikes are compatible with the same roughly north-south bulk shortening direction. A few shear zones have an irregular, non-planar geometry and are filled with almost undeformed microgranite. These are interpreted as the first expression of shear localization in the Pluton. At low temperature, deformation localized as shear zones of predominant sinistral sense affecting the granodiorite and the leucocratic dikes. Shear zones range from meter-thick white mylonitic bands and associated shear bands on the left to millimeter-thick discrete shears as in example on the right. Displacement associated to shearing can be determined from shear dikes. The slide shows a shear strain analysis across an area affected by inhomogeneous post-dike shearing. Mean shear strain value of 2.7 has been calculated using total width versus total displacement relationships. Shear zone displacement width ratio, measured in different sized shear zones, is of about 1 order of magnitude and 1 order of magnitude greater than Mitra 1979 data from higher temperature shear zones in the Appalachians.
At the pre-shearing state and as a result of pre-full crystallization deformation, that is, submagmatic deformation, granitoids exhibit elongated enclaves with a mean strain ratio of 2.7. Within the mylonitic bands, the enclaves are extremely elongated up to strain ratios of 100 to 1. Sets of conjugate strike-slip fractures cross-cut mylonites, postdating ductile shearing. Note that the roughly north-south shortening direction is similar and coherent with the orientation required to develop the initial magmatic fabric, the direction of dike emplacement, and the later shear zones. The analyzed structures has allowed us to reconstruct the whole history of the Pluton, from sigmagmatic homogeneous deformation to dike intrusion at high temperature solid state to low temperature solid state, localized heterogeneous ductile to brittle shearing.
We will now move to the northern shear belt, where shear zones mainly cross-cut medium to high-grade schist, that is, foliated rocks. At the map scale, the shear belt appears as a complex network of anastomosing mylonitic bands, depicted in green, across the schist with variably oriented previous schistosity, the so-called S1 or S2.
A major difference between the northern and southern shear belts regards the nature and inherited internal structure of the lithologies affected by the shearing event. A spectrum can be defined from isotropic crystalline rocks such as undeformed granitoids to highly anisotropic rocks such as phyllites and schist. The lithomechanical units of the southern shear belt correspond to the left side of the gradual range, whereas those of the northern shear belt are broadly represented in the right side. The slide shows a representative example of shear zones of the northern shear belt. They develop in green schist facies metamorphic conditions and cut across mid to high-grade foliated schists which conform the dominant lithology. Although the northern shear belt mainly involves schist, they can also cross-cut lesser anisotropic rocks such as these orthogneiss. Less crystalline schists give rise to faults with sheared limbs, a transitional structure between shear zones and faults.
Apart from cutting across mid to high-grade schist, the northern shear belt also locally affects the so-called migmatitic complexes, where before the D3 event, high-grade schists were transformed into migmatites and intruded by different types of granitoids. On this map, part of a migmatitic complex is represented in the northeast corner. These banded mylonites are the result of strongly sheared migmatites, granitoids, and pegmatites. They are dramatically exposed along large shear zones like the rectangle one. The pegmatite dike swarm, intrudes syntectonically during D2 event, is also heterogeneously affected by D3 shear zones. The shear zones that form this complex anastomose network are predominantly northeast dipping. They can be grouped into two sets, a main set of northeast dipping shears with dextral reverse shear sense and another north-northeast dipping set with sinistral normal movement. Earlier D2 faults are deflected towards the shear zone boundary and completely transposed in the interior of the myelonitic band. These shear zones will be analyzed in terms of individual geometry, kinematics, and progressive development. Their arrangement into an anastomosing network will also be addressed to finally focus on the variety of shear zones-related structures.
This is a detail of the famous Calaprona shear zone. It is a magnificent example of progressive dextral deflection of the previous S2 foliation in the schist towards parallelism with the shear zone. It is also an ideal place to determine deformation parameters and fabric variation along and across shear zones. This sketch represents a theoretical profile assuming 2D simple shear and passive deformation. Notice that at low and moderate shear strain values, the deforming previous foliation does not track the XY plane of finite strain.
Let's now compare the 3D arrangement of the deflecting foliation in shear zones developed in isotropic versus foliated rocks, assuming simple shear and passive deformation. While in initially isotropic rocks the angle between the shear direction Lx and the vorticity axis W is of 90 degrees, in shear zones affecting previously foliated rocks this angle may vary from 90 to 0 degrees. This is because in previously foliated rocks the vorticity axis W is given by the intersection line between the pre-existing foliation and the shear plane, SSZ. We show two possible configurations of the whole 0 to 90 degrees spectrum. We can also point out that the smaller the angle between the vorticity vector and the shear direction, the larger the range of sections which show an apparent movement contradictory to the true movement.
Here we show the 3D arrangement of the Calaprona shear zone. In this case, the angle between the stretching lineation LM and the vorticity axis is about 60 degrees.
However, due to the fact that the pre-existing foliation had a variable orientation before the shearing event and that the shear zones themselves also develop in a range of orientations, the Cap de Creus shear zones display different angular relationships between the stretching lineation L and the vorticity axis W. In one, the angle is of 79 degrees, in two is of 30 degrees, and in three is of 13 degrees. Notice that in 3, the horizontal outgroup section will show a false shear sense. Are the shear zones compatible with the heterogeneous simple shear model? Although studied shear zones in foliated rocks approach a simple shear model, some deviations occur. Towards the shear zone interior, the formation approaches simple shear. Shear zones nucleate and develop induced by the presence of inherited lithostructural configurations. Among the most frequent processes leading to shear zone development, we will focus on the following three. 1. Buckling instabilities in anisotropic rocks, that is S1 or S2 previous foliations. 2. Ductile shear reactivation of pre-existing fractures such as a joint network. 3. Shear localization due to strong rheological contrast between different lithologies. Distinguishing between these different processes from field geometries is not always straightforward. That is the case of this image, which brings us the chicken and egg dilemma of what is first, the buckle or the fracture.
The structure in this picture could be a good candidate for a shear zone related to a buckling instability. The previous anisotropy, defined by a penetrative layer, parallel foliation, and quartz lenses, is folded with shear localized in a limb.
In the upper model, simple shear conditions are maintained across the shear zone, which imposes the condition of no transverse shortening. Shear strain is partitioned through layer parallel shearing or less competent darker layers and coaxial stretching along the more competent lighter layers. In the lower model, shearing is also partitioned by shear along the less competent dark layers, while the competent layers rotate without coaxial stretching. Under such conditions, shear zone parallel thickness increases towards the shear zone interior.
Mechanical anisotropy induces buckling perturbations. An incipient shear zone in Cap de Creus shows the increase on shear zone parallel thickness in agreement with the model proposed. The propagation of this anisotropy-induced instability can also create fractures. Ductile and brittle deformations proceed simultaneously, but according to this model, the initial deformation pattern obeys to a buckling instability. The preliminary model for shear zones forming as buckling instabilities in mechanically anisotropic rocks consists on shear zone initiation as a flexural fault evolving toward shear localization on the rotated limb.
Continuing the 2D approach, identical profiles with no area change, that is, no volume loss, imply that the formation should respond to heterogeneous simple shear, according to Ramsey and Graham, 1970. Lateral strain gradients impede shear zones to correspond to simple shear, according to Carreras, 2000. This drawing shows an heterogeneous subsimple shear zone with a shortening component normal to the shear plane. Under such circumstances, transverse profiles are not identical. Note that laterally, shear zones vary from sharp boundaries on the left to smooth boundaries to the right. The two photos correspond to the same shear zone margin.
Pre-existing foliation causes the nucleation of king-like conjugate shear zones. It is reasonable to assume that such instabilities are governed by buckling processes.
Besides the fact that pre-existing foliations cause the nucleation of buckling instabilities leading to most shear zones, we can additionally consider the likely role of pre-existing fractures in the nucleation of ductile shear zones. In this detail, you can see small ductile deflections at the margins of a pre-existing joint normal to the foliation. These fractures do not have to be shear zone precursors, but just structural discontinuities inherited from an earlier event. And here you have another example of fractures perpendicular to layer and foliation that laterally grade into ductile shears. Analog experiments with the BCN stage show how initial fractures at a high angle to layering can propagate as ductile shears. Shear zones may also form due to competence contrast between rheological heterogeneous rocks. Shear tends to localize in the less competent rocks. In this example, a dextral shear zone is localized in pegmatitic schist at the boundary with a strong body of pegmatite.
Strong rheological contrast within a multi-layered sequence can produce an extreme strain partitioning, leading to geometrically and kinematically complex shear zones. This is the case of the complex structures developed within a marble metapsamite multi-layer unit in the northern Cap de Creus shear belt. Zones of high ductile strain localized in the marble layers, represented in blue in this drawing, corresponding to the previous picture. Marbles exhibit complex folds, whereas metasamites show mostly brittle boudinage structures. These structures strongly contrast with coeval, discrete shear zones developed in the surrounding migmatitic schists.
A closer look into the layered marbles shows the symmetric folds of west versions, to the left, compatible with layered parallel sinistral shearing.
Sinistral layer parallel shearing causes boudinage of the metapsamite and calc silicate layers. Asymmetric boudins are delimited by a west-down set of synthetic fractures. The interlayered marbles accommodate the slip along fractures by ductile flow.
The kinematics of the multilayer is compatible with the bulk layer parallel sinistral normal movement, which contrasts with the prevalent dextral sense of the shear zone network developed in the surrounding metasamites. These two sketches show the structural evolution of this case study, before and after the D3 deformation event. Bulk non-coaxial deformation is partitioned between highly contrasting lithological units in mode of deformation, brittle versus ductile, strain magnitude, high strain versus low strain, vorticity, pure shear dominated versus simple shear dominated, and kinematics, dextral versus sinistral. Consequently, caution is needed when interpreting regional tectonics in highly partitioned domains associated with rheological heterogeneities.
We will now center our attention on the assemblage of shear zones into anastomosing networks.
Such anastomosing patterns usually result from the intersection or confluence of two or more individual shear zones, such in this mid-scale example. In this case, merging of two shear zones of opposite shear sense gives rise to the so-called SIPA junctions by Pasquier and Platt 2017. Partitioning of ductile deformation into anastomosing shear zones produces lozenges. Lozenges are less deformed elongate bodies bounded by the shear zones. The bounding shears can be either of equal or opposite shear sense. The Cap de Creus case study shows the relevance of the orientation of the previous foliation in controlling the orientation and propagation of shear zones, and therefore in the prevalent mechanism of lozenge formation. As the bulk kinematics is the same along the investigated areas, that is a dextral simple shear dominated regime, it can be confirmed that the foliation orientation plays an important role on the orientation of the shear zones. This fact will be now illustrated with field examples. In domains where the initial angle alpha 0 goes between 45 degrees and 90 degrees, the formation partitioning gives rise to two sets of conjugate shear zones oriented symmetrically with regard to the previous foliation. This mechanism takes place in domains where the dominant previous foliation is subparallel to the instantaneous shortening direction. Thus, the layering foliation embedded by the conjugate shears drags and shortens to form oppositely concave folds that resemble the typical millipede structures described by Bell 1981. In this model, the previous host foliation is subjected to progressive extension, being oriented close to a plane of maximum shear strain. In this case, lozenges preferentially initiate by linkage of individual principal synthetic shear zones throughout secondary antithetic shears that propagate subparallel to the preexisting foliation. The mechanism is analog to the domino or bookshelf mechanism, in which bulk shearing is partly accommodated by synthetic rotation of blocks through antithetic shears, that in this case study are parallel to the foliation and have a sinistral sense. In other domains where a myelonitic shear zone related foliation is developed or where the previous foliation originally makes a very small angle with the bulk shear direction, instabilities can arise, originating secondary synthetic shears. In this simplified map of the northeast Cap de Creus Peninsula, we have indicated two distinct areas of shear zone localization and evolution. In Cala Culip, where the pre-existing foliation trends north-south, the overall northwest-southeast dextral range-dominated transpression generates conjugate shear zones. Under continuous shearing, the antithetic set will rotate and become gradually less active. It may even invert the sense of shearing during the late stages of its evolution, giving rise to kinematically complex shear zones. Under the same D3 tectonic regime, in Cala Prona, where the previous foliation trends close to east-west, a set of dextral shear zones will become prevalent. Progressive deformation results into two sets of dextral shears. Here we present a two-dimensional interpretation for the localization and evolution of the northern Cap de Creus shear zones based on the two former cases, and assuming a northwest-southeast range-dominated bulk transpression controlled by the orientation of the pre-existing planar anisotropy.
We will now deepen into shear zone-related structures. A variety of structures are present in the interior of shear zones. Shearing induces the development of banded and strongly foliated myelonites whose orientations are closely parallel to the shear plane. Tectonic fabrics are predominantly planolinear with generally well-marked stretching lineations, specially developed in quartz-rich layers and myelonitic quartz or quartz feldspathic veins. The analyzed zones indicate that neither the amount of shear strain nor the presence of local mechanical instabilities are a general cause inducing a band closely parallel to the shear plane to shorten and fold. If there is no flow perturbation, bands extend homogeneously or develop pinch and swell structure if there is a rheological contrast. However, internal structures at the shear zone interior are far more complicated than if this corresponds to an heterogeneous simple shear deformation. An interesting aspect is that myelonitic bands can experience both extension and shortening, indicating lateral and transversal strain partitioning. As shear-associated stretching proceeds, the presence of rocks with competence contrast leads to the formation of boudinage or pinch and swell structure, which are often asymmetric. Dextral shear band type boudinage in quartz is shown in the upper photo, and the dextral sigmoidal pinch and swell of a myelonitic pegmatite in the photo below.
This amazing pinch and swell of pegmatite at Cala Serena Creek really has many fans.
Here, you can observe a boudinage tourmaline crystal in a protomyelonitic pegmatite. Inclusions of other stiffer lithologies inside shear zones often display an asymmetric shape. But kinematic interpretation often requires a detailed analysis. This is a 2D detailed map of a lozenge of calcilicate rock in green inside a deep slip shear zone affecting schist in purple and pegmatites pink. The delta-shaped lozenge of calcilicate rock display an apparent anticlockwise rotation. The stereo plot and the 3D sketch shows the attitude of the lozenge, internal foliation, the myelonitic foliation, and the stretching lineation. Note that since rotation axis is closely parallel to the shear direction, the observed delta-shaped structure is not kinematically reliable. Shear bands, also called extensional crenulation or extensional shears, are common deformation localization structures. They are particularly common in phenolites, such in these two examples of extra shear bands. Their formation does not depend on reaching high shear strain values, but on the presence of flow perturbations induced by changes in the shear direction or sense. They are good shear sense indicators when viewed on sections perpendicular to foliation and parallel to the shear direction. Shear bands similar to kinks usually display a complex 3D arrangement. In sections parallel to the stretch inclination, LM, a single set of synthetic shear bands is observed, while on sections normal to the stretch inclination, two sets may appear. These more brittle shear bands are developed in myelonitic quartzites, synthetic shear bands above and antithetic below. Shear bands form at the shear zone interior but also at the margins. Their orientation depends on the relative orientation of anisotropy planes and the instantaneous stretching axis. Two sets, one synthetic, the other antithetic, form where the extensional ISA is closely parallel to the foliation. In domains where the foliation makes an angle of approximately 30 degrees with the shear plane, only the synthetic set is active and the shear bands are almost parallel to the shear plane. Towards the shear zone interior, shear bands are oblique to the myelonitic foliation. Thus, their orientation changes gradually.
Explanation of the former structural arrangement is based on experiments on mechanically anisotropic materials. Depending on the relative orientation of the rock anisotropy with the bulk deformation axis, shortening, extensional, or both types of instabilities will form. Type and geometry of the developed structures is controlled by the relative orientation of the instantaneous stretching axis with respect to the previous layering or foliation. Thus, the dichotomy between C and C' planes is arbitrary, as the shear band pattern simply reflects a particular angular relationship between the instantaneous stretching axis and the rock anisotropy. In a similar way that the orientation and symmetry of shear bands are controlled by the geometrical relationships between the instantaneous stretching axis and the anisotropy, for instance the foliation, quartz-axis fabric shows a gradual rotation of the girdle and increasing asymmetry. Note that quartz fabrics passes from an orthorhombic cross-girdle pattern to a single asymmetric girdle. Both facts evidence the inappropriate use of shear band orientation on quartz fabrics to infer the deformation regime or vorticity.
Shear-related faults are very common in shear zones. However, these faults may have different origins. Some can be sheared pre-existing faults. Others are faults formed during the shearing event. One should distinguish between faults affecting the pre-existing foliation and those that follow the myelonitic foliation. Concerning the first, in a 2D simplified approach, shearing of pre-existing surfaces originates the growth of instabilities which can develop into contractional structures like faults and crenulation if the initial orientation lies in the shortening field. Shortening occurs at the initial stage affecting the pre-existing foliation, bearing S1 in this example. Increasing strain will be followed by layer extension, but the initial folding structure are usually preserved. In a 3D approach, layer and foliation can undergo simultaneous shortening and extension controlled by the sectional ellipsoid. Faults nucleate with hinges parallel to the x-direction of the sectional ellipsoid. Increasing shear causes faults to flatten and to rotate hinges towards parallelism with the shear direction. This makes a relevant difference with the 2D approach because after a certain amount of shear strength reached, hinges will be parallelized with the shear direction and not normal to it as in the 2D approach.
This slide shows field photographs of faults developed on a pre-existing foliation involved in a shearing event in the northern Cap de Creus shear belt. Faults developed at the margins of shear zones cutting across schists. These are the result of non-passive shearing of anisotropic heterogeneous rocks, for instance foliated rocks, as shown in the previous slide. On the right photo, faults are located on a low shear domain, while the left one shows tightened faults as a result of intense shearing.
Now we will examine another category of shear-related faults. These include faults that affect the myelonitic foliation and bands formed as the result of a significant extension. Although in ideal shear zones myelonitic foliation and bands would indefinitely stretch, however, faults affecting the myelonitic banding and foliation are common. These two examples show faults affecting myelonitic quartz bands. In both cases, shearing is top to the right.
Intramyelonitic faults are those that nucleate on myelonitic bands, like in these two previously stretched pegmatite dikes. Pegmatites first became banded and acquired an internal foliation. Flow instabilities may cause the subsequent folding. These examples show two aspects of these faults. In the left photo, there is a wavelength decrease with thickness of the myelonitic pegmatite. This example was used in Huddleston and Trigger's 2010 paper. The photo on the right shows another folded myelonitic pegmatite, evidencing a thinning of the reverse short limb, which is a common feature of intramyelonitic faults. In both cases, shearing is top to the right. Fault hinges display variable orientations with regard to the shear direction. Fault hinges from the mapped area are plotted on the stereo plot. The blue dot indicates the mean orientation of the stretching lineation. The angle between fault hinge and the shear direction decreases with increasing fault tightening. The lower picture shows faults with hinges at a high angle to the stretching lineation, whereas the upper photo corresponds to faults with hinges parallel to the shear direction. It is assumed that fault hinges at high angles to the shear direction represent early stages of fault evolution.
This 3D sketch shows the variability of fault hinges and related asymmetry, and in B, the corresponding stereo plot. Figure C applies to the case shown in the previous slide, where in 1973 the separation angle method of Hansen was applied and coherent results were obtained. That is, the plot of stretching lineations coincides with the asymmetry change.
This picture is a view from above a myelonitic quartz band. Incipient faults show hinge orientations at a high angle to the shear direction, a situation which is very common in the initial stage of intramyelonitic faults. Contrarily, initial orthogonality is less common. The fact that fault hinges are mutually subparallel indicates that faults form from instabilities affecting the entire band rather than resulting from punctual instabilities. The initial orientation of the hinges is governed by the incremental sectional ellipse that, in its turn, depends on how the perturbated flow plane is oriented with regard to the previously stretched myelonitic quartz band. It is well known that parallelization of fault hinges with the shear direction is achieved through hinge curvature, ultimately leading to sheath fault development. Again, as previously analyzed for the marginal faults, the evolution of intramyelonitic faults involves the deformation and rotation of the hinge towards parallelism with the shear direction. Thus, While the 2D approach seems to point towards the unfolding possibility, this is not the case when one takes into consideration hinge rotation. In this, and in other similar cases, it is important to take into account that fold analysis using fold profiles involve an area reduction. The final stages of intramyelonitic folds are flattened isoclinal folds with hinges parallel to the shear direction. These folds behave as coarse bands that can subsequently initiate a new folding process. This gives rise to fold superposition. In the here exposed example, 3 generations of folds can be recognized. Apart from folding, boudinage structures, and shear bands, other tectonic features can be related to the shear zones. This is the case, for instance, of pseudotachyllites. Although not very common, pseudotachyllites can be present in shear zones as vein networks cutting across the myelonitic foliation. To finish this video, insight into some microstructural features related to shear zones will be given now. The schists contain abundant veins and nodules, of course segregated during the prograde metamorphism previous to the shearing event. Quartz of these bodies is coarse-grained, centimetric grain-sized. When approaching a shear zone, all grains exhibit signs of abundant deformation accommodated by formation of subgrains and recrystallization with development of new grains of about 100 microns. Gradually, all grains elongate and are consumed by the developed new grains. The final myelonitic quartz exhibits a strong crystal-preferred orientation, while shape-preferred orientation is absent. Feldspars from pegmatites also become deformed when sheared. These are 2 examples from a protomyelonitic pegmatite. K feldspar on the left shows a slight microplasticity, deformation visualized by the undulatory extinction, and an important cataclasis. Plesioclase shows evident microkinks of the twinning, followed by cataclasis. In this slide, the microstructure of a strongly sheared pegmatite evidences the cataclasis of feldspars, giving rise to porphyroclast, while quartz deforms plastically via dislocation creep and an associated recrystallization. Undisturbed quartz myelonite show a quartz C-axis fabric consisting on an asymmetric girdle coherent with the shear sense. The stereoplots on the left show the gradual development of the fabric from low sheared domains 1, 2, and 3 towards the shear zone interior 5 to 7. In a similar way that it happens to the quartz ribbons that often become subsequently folded, quartz fabrics become altered when a quartz band is folded. The APA diagram A shows fabric modification across asymmetric folds with hinges normal to the shear direction. Once the folds become parallel to the shear direction, the original fabric is regenerated and no change of fabric is detected around the fold. Note that all fabrics patterns correspond to fold profiles normal to the fold hinge. While in A, shear is parallel to the screen, shearing is top to the left, in B, shearing is perpendicular. Thank you very much. If you want more information, apart from the large number of papers, we have a field guidebook on the geology of Cap de Creus. Also, you can contact us for a guided field trip.